Good morning. Myself Dr. B.Samuel Jacob, Assistant Professor, Department of Biotechnology, School of Bioengineering. I'm going to present my projects for the SRM Phoenix Project Award pertaining to World Environment Day competition. As you know, in the present scenario, waste management is becoming a huge challenge in the global context, where the problem starts with the initial segregation to the final disposal at the landfill site. So we started to address the problem where the solid waste, efficient solid waste management in the rural villages. So the first project I would discuss about is the versatile anaerobic reactor for household to yield biogas by utilizing waste shortly called as volume in Sanskrit is known as gas. Government of India has started to disseminate the rural family-sized biogas plant three decades before, where a small, robust kind of biogas plant without any appropriate technical inclusion were being disseminated, where slowly it started to provide a lot of problems like inefficient biogas production and non-conversion of waste to proper biogas. The problem that we found out is the paste formation due to improper mixing. As you can see in the middle figure, where the solids has been upraised to the top of the reactor due to the pressure changes that happens inside. These solid particles start to clog the biogas pipes where the biogas can escape from the reactor. Second thing, the microbes cannot able to access the solid as it has been upraised to the top of the reactor. So there is a need of mixing. To address this problem, we design a manual pedaling type bioreactor where a person, if he pedals outside, the contents in the reactor can be mixed properly. So we have optimized in our laboratory that about 12 minutes of mixing in morning and evening could provide an efficient mixing inside the biogas where the resultant yield could be 1.5 to 2-fold higher as compared to the unmixed bioreactor. So this concept was financially supported by Unnat Bharat Abhiyan, Ministry of Human Resource Development, and we have designed a 500-liter biogas plant and provided to the beneficiary in the adapted villages by SRMIST. In order to utilize a recent technology in this traditional biogas plant, we have incorporated the IoT technology for the monitoring purpose. That is the second bottleneck in the rural biogas plant because the end user is not technically adequate enough to handle the biogas plant because it has a lot of technical aspects involved. So, for example, when the biogas plant reaches an acidic level, there won't be any biogas formation because the microorganisms prefer the neutral range of pH. So, in order to avoid it, we have incorporated sensor-based technologies where the parameters like pH, pressure in a bioreactor, along with the methane concentration, can be captured and can be stored in the cloud through the IoT technology, and it can be transmitted to the ground station, that is SRMIST. So what happens when the biogas plant shows any fluctuation in the pH or the improper biogas production, that can be immediately monitored in the real time and the problem can be addressed immediately. That is one of the prime focus because the more the late of the addressal of the problem, more will be the reversibility of the problem. So, and also another advantage of this IoT is that we can integrate all the biogas plant in a village as a cluster where we can monitor different biogas plants installed in different locations of the villages in a single real-time location in SRMIST. So this is one of the technologies that we have developed, and the technology has been technology has been transferred to the end user through the UBA, and now we are in a collaboration, collaboration with an NGOs to widely disseminate throughout the nation, and the patenting is in the progress. Second project is about IB technology. As I told earlier, the problem in the waste handling started from the inception itself. That is improper segregation in our households or in the municipal sites causes a huge havoc in the segregation when it is being disposed in the landfill site. What happens? Improper segregation resulted in the culmination of both degradable and non-degradable waste in the landfill that won't be degraded appropriately, resulting in a recalcitrant nature. So for that, we have designed a intelligent build technology. Even though there are technologies are available to measure the real-time location of the dustbins, this is an advanced level where the waste can be sensed using the sensor, and the bin can segregate the degradable and non-degradable waste material that are present in the pile of waste. So this is a bottom-up approach where we have incorporated the sensors for the metals, glass, papers, etc. And those that escape these sensors all the degradable waste. We are the four compartments in this I bin where the different types of waste materials are being collected depending upon the sensor. This concept has been recognized as one of the top 20 innovation by the best able, that is Association of Biotech-led Enterprises, Department of Biotechnology, Government of India. Second thing is the proper utilization of agro residues. So as we know, the plastic disposal is becoming a huge problem. Last year, Government of India and also the Government of Tamil Nadu has prohibited the use of single-use plastic tablets and plastic covers that are being used in the grocery stores. So we have ventured into a product. Why can't we create a bioplastic out of the agro residues itself? For this, we have chosen the 4 different agro residues that starts from fish scales from the fish markets, the soya whey that is separate from the soya milk preparation industries, spent tea powder, and aloe vera reprint after the gel extraction, the outer portion of the reprint. So what we did, we isolated the protein out of these agro residues, and we fabricated a bioplastic using a novel technology where it is called as conglomerized bioplastic. So far, there is no technology available for the conglomerization of different proteins from different agro residues. Only there are technologies are available to prepare bioplastic from the starch and the protein as a sole polymer. So we have fabricated this conglomerized bioplastic, and we obtained a good quality of bioplastic that are mostly equivalent to the commercial bioplastic. So you can see here the commercial plastic material that are presently available in the normal grocery stores, where it is sold as the compostable biogas plant, is obtained from the starch from the tapioca plant. And we have fabricated this waste derived bioplastic, and we tested it in the standard testing laboratory in the CLRI, and it could capable of the tensile strength is about 4.9 megapascal, so which is almost equivalent to the commercial bioplastic that are available in the market. The difference between these two is that the commercial bioplastics that are available in the present market is from the food crops, that is the tubers, tapioca, whereas the bioplastic that we obtain from our laboratory is from the waste residues. The advantage of incorporating the tea powder here is that you can obtain a non-transparent bioplastic. Sometimes when you want to cover a light-sensitive food material, you need a bioplastic material that should be translucent in nature. So this tea powder, the natural phenolics provide a darker color that provides the translucent nature of the bioplastic. So this patent is also under progress, and we are now thinking to collaborate with the bioplastics manufacturing industries to convert the waste to the bioplastic material. And the fourth project is the aloe vera leaf print to bioethanol. This is something like waste to fuel production approach, where, as you know, the aloe vera, after the gel extraction is being taken, that is a commercial product, the aloe vera leaf print that is profusely rich in the cellulose and hemicellulose content that can be tapped for any useful purpose. So we have routed these aloe vera leaf print as it is rich in the cellulose and hemicellulose, shortly called as polocellulosic component, for bioethanol production using the in-house enzymes. We have designed the enzyme production in our laboratory using the locally available isolates of microorganisms, locally available waste resources like coconut oil, rice straw, sugarcane bagasse, for the production of the enzymes that are being incorporated for production of bioethanol from this. We utilize the yeast for the production of bioethanol. The problem here in the aloe vera leaf print is the outermost lignin layer that is not important for the bioethanol production, which protects the cellulose layer. So we need to delignify it before we access the polocellulosic compound. For that, we use the lactase enzyme obtained from the in-house enzyme production system, that is also from the agro residues only. And once the lignin is being removed, the cellulose and hemicellulose content being tackled by the cellulase enzyme produced by the local isolates aspergillus that we have isolated and used for cellulose production, and we could able to achieve about 65% of saccharification. That is almost at par with the present bioethanol production approaches. And this outcome of these results has been published recently in the Industrial Crops and Bioproducts Impact Factor 4.19, thereby standardizing this aloe vera leaflet as one of the industrial crop where the gel is a commercial product. Now, as Government of India is promoting the Ayush scheme, where this aloe vera play a prominent role, whereas we are neglecting the waste obtained from it. This approach can able to overcome a circular bioeconomy approach, thereby the waste can be converted to a bioethanol that can be used as a commercial product also. And we have used the non-biological system like microwave assisted to increase to shorten the time and to increase the process efficiency. That also we found it is an efficient process. These two papers are being recently communicated and been accepted in a reputed journal. And fifth project that I'm discussed about is the water acids that are being preferred in the most of the natural river bodies, lakes, and also the agricultural ponds. That causes a huge problem of depletion of dissolved oxygen in it, and thereby resulting in the destruction of flora and fauna. So what we have done is that we have extracted this water acid and utilized it for biogas production. That is first stage to produce the biogas. After the biogas production, because it is very rich in water content, so it is very natural to undergo subjecting to biogas production. Once the biogas production gets over, the residues we have subjected for pyrolysis process to obtain a bio oil that can be mixed with any conventional agricultural engines as a blending material, where we found that the calorific value is at par with the conventional pyrolysis oil. And the other residue obtained for pyrolysis is the biochar, that is enriched with the nitrogen, phosphorus, and potassium, that can be applied as a fertilizer. And you can see the flaming property of the bio oil obtained from this pyrolysis process. The left side dry cloth is after ignition, and the same dry cloth is being wetted with this bio oil and then given ignition. You can see the calorific power of that particular bio oil. Thereby, this way water acid can be re-established as a resource for fuel and fertilizer. Now the fertilizer field trial is under progress in our SRM itself, and we hope we could able to produce the fruitful result out of it. And herewith, I'm concluding my presentation, where we are in a path where all the waste resources are being utilized from to wealth purpose, either as a fuel, fertilizer, or as a commercial value-added process, thereby attaining the sustainable goal endowed by the United Nations Organization. Thank you for the opportunity.